Picture the night sky, every star you can see, every faint smear of light from a distant galaxy, every point of brightness scattered across the darkness above you, all of it is temporary. Every single one of those lights will go out, not just the stars visible to the naked eye, not just the ones in our galaxy. Every star in every galaxy in the observable universe will eventually exhaust its fuel, cool down and go dark. And when the last one finally dies, the universe will not end. It will continue for longer than you can possibly imagine. In a darkness so total and so permanent that the billions of years of stars and light and heat that came before it will amount to less than a single breath in a story that has no final page. The universe is not going to end in fire. It is going to end in silence, in cold, in a stillness so absolute that the word stillness does not begin to describe it. And the physics that guarantee this outcome are not speculative. They are among the most firmly established laws in all of science. The universe has a death sentence written into its own rules, and it was written on the first day. Let us start with what that sentence actually says, because most people have heard the phrase heat death of the universe without really understanding what it means. And what it means is genuinely one of the most unsettling things physics has ever produced. The second law of thermodynamics states that in any closed system, entropy always increases over time. Entropy is a measure of disorder, of the dispersal of energy. When energy is concentrated, when it sits in a hot, dense place, surrounded by cool, empty space, it can do work. It can power a star, drive a chemical reaction, fuel a living cell. But energy always flows from hot to cold. It always spreads out. It always seeks equilibrium. And once it reaches equilibrium, once heat is distributed perfectly evenly across the entire system, no more work can be done. Not because energy has been destroyed. Energy is never destroyed. But because work requires a difference in temperature, a gradient, a place where things are hotter than somewhere else. When everything is the same temperature, that gradient disappears. The energy is still there. It is just useless. Permanently, irreversibly useless. That state, the state of maximum entropy, of perfect thermodynamic equilibrium, is what physicists call heat death. It is not a fire. It is the opposite of fire. It is the final, absolute, inescapable stillness of a universe that has run out of differences. The universe began in the lowest entropy state imaginable. The Big Bang concentrated all of the energy that exists into a single point of incomprehensible density and temperature. Everything since then has been the slow, inevitable unwinding of that initial concentration. Stars are just a stage in that unwinding. They form when gravity pulls hydrogen together until fusion ignites, converting that gravitational potential energy into light and heat. They burn for millions or billions of years, pouring that energy outward into space, and then they die. And the energy they released disperses further and further, becoming more evenly distributed, less concentrated, less useful. The universe has been moving toward heat death since the moment it began. We are living in the middle of that process, in the brief cosmological window when stars exist. And that window is closing. But how much time are we actually talking about? This is where the numbers become almost impossible to hold in your mind. The universe is currently about 13.8 billion years old. The Sun has roughly 5 billion years of hydrogen fuel remaining. Most stars in the galaxy are smaller and dimmer than the Sun, and they burn their fuel far more slowly. The smallest stars, called red dwarfs, can burn for up to 10 trillion years. That is 10 followed by 12 zeros, about 700 times the current age of the universe. The era of stars, the period in cosmic history when nuclear fusion lights up the night sky, will last roughly from the Big Bang until about 100 trillion years from now. After that, no new stars can form because the raw material has been used up or scattered too thinly to collapse under gravity. The last red dwarf will slowly cool and fade, and then there will be nothing burning anywhere in the universe. But the universe will still be far from over. Astronomers who study the deep future have divided the timeline after the age of stars into distinct eras, each one lasting incomprehensibly longer than the one before it. The first of these is called the Degenerate Era. It begins when the last star dies and ends when the last white dwarf has cooled to a black dwarf and the last neutron star has decayed. This era lasts from roughly 100 trillion years to about 10 to the power of 40 years from now. During this period, the universe is not completely dark or completely quiet. Occasionally, brown dwarfs, the failed stars that never quite ignited, can collide and merge, briefly reigniting a dim and short-lived fusion reaction. Occasionally, a rogue planet drifting through the void falls into a black hole and releases a brief flare of energy. Occasionally, two dead stellar remnants collide in a violent event that briefly illuminates the surrounding darkness. These events are extraordinarily rare, separated by billions of years of silence, but they happen. The Degenerate Era is not total darkness, it is something worse. It is a universe where light is the exception, where warmth is a temporary accident, where the distances between events are so vast that no observer could possibly witness more than one in a lifetime. If any civilization survived into the Degenerate Era, it would look out at a sky containing no stars, only the occasional faint glow of a cooling white dwarf receding into invisibility over trillions of years. The constellations we know would have dissolved billions of years earlier as stars drifted apart on their separate paths through the galaxy. The galaxy itself would have changed beyond recognition, its spiral arms long since dispersed, its stars scattered into a diffuse and cooling halo. The sky would be dark in a way that no human eye has ever seen darkness, because even at night on Earth, the sky is full of starlight. In the Degenerate Era, there is no starlight. There is only the slow, cold dying of the remnants. After the Degenerate Era comes the Black Hole Era. By this point, all ordinary stars are gone. What remain are the dense remnants left behind by stellar deaths. White dwarfs that have cooled into invisible black dwarfs, neutron stars and black holes. Of these, only black holes survive into this era as genuinely stable structures. Everything else has either cooled to invisibility or, if proton decay is real, dissolved entirely into radiation. Black holes are the last structures standing, and even they are not permanent. And this is just the beginning of the deep future. Protons, the fundamental particles that make up the nuclei of atoms, may not be stable forever. Certain theories in physics predict that protons decay over extraordinarily long timescales. The current experimental lower bound on the proton lifetime is around 10 to the power of 34 years. If protons do eventually decay, then all ordinary matter will slowly dissolve into radiation and lighter particles. The process would complete on a timescale of roughly 10 to the power of 40 years, far longer than the proton's individual lifetime, because matter is so spread out by then that even slow decay takes an immense amount of time to run its course. At that point, there is no more ordinary matter anywhere in the universe. What is left are black holes and the faint, cold radiation produced by everything that came before. Black holes are the last structures standing, and even they are not permanent. In 1974, physicist Stephen Hawking made a discovery that changed our understanding of black holes entirely. He showed that black holes are not perfectly black. Due to quantum effects at the event horizon, they slowly radiate energy in the form of what is now called Hawking radiation. The process is extraordinarily slow. A black hole with the mass of our Sun would take approximately 10 to the power of 67 years to evaporate completely through Hawking radiation. The supermassive black holes at the centers of galaxies, with masses billions of times greater than the Sun, would take roughly 10 to the power of 100 years to evaporate. That number, 10 to the power of 100, is called a googol. It is incomprehensibly larger than the current age of the universe. But it is not infinite. Eventually, every black hole evaporates. The last one releases its remaining energy in a final burst of Hawking radiation, and then it is gone. At that point, roughly 10 to the power of 100 years from now, the universe contains nothing but a thin, cold, perfectly uniform gas of photons and leptons, spread across an incomprehensibly vast space, all at the same temperature, just barely above absolute zero. There are no structures, no gradients, no concentrations of energy anywhere. The entropy of the universe is at its maximum. No more work can ever be done. No more complexity can ever arise. The universe has reached heat death, and it will stay there, unchanged, for an eternity that makes everything that came before it seem like a single instant. This is not a hypothesis. It is the logical consequence of two things we know to be true: that the second law of thermodynamics is real, and that the universe is finite in its energy resources. Every star that has ever burned, every galaxy that has ever formed, every planet that has ever circled a warming sun, has been a temporary eddy in a river that has always been flowing toward this end. We exist in that eddy. We are a consequence of the universe being extremely far from equilibrium, of there being enormous differences in temperature and energy density between the hot, dense stars and the cold, empty void around them. Those differences power everything: chemistry, biology, thought, civilization. All of it runs on gradients, and all gradients eventually flatten. But here is where it gets genuinely strange, because the heat death of the universe is not the end of time. It is the end of meaningful time. After heat death, the universe continues to exist in a state of perfect equilibrium. Nothing happens. Nothing can happen. There is no process by which one moment differs from the next. In a very real physical sense, time as we experience it, as a sequence of events and causes and effects, ceases to have meaning. There is still a future. It is just identical to the present, and the present is nothing. Not darkness in any dramatic sense, not silence in any poetic sense, simply a cold, uniform, featureless expanse of maximum entropy that will persist without change for longer than any number we have words for. There is one more complication that makes the heat death even more final than it sounds. The universe is not just expanding, it is accelerating. Dark energy, the mysterious force driving that acceleration, means that distant galaxies are not merely moving away from us, they are moving away faster and faster over time. At some point in the far future, galaxies that are currently visible to us will be moving away faster than light can cross the distance between us and them. They will disappear beyond what cosmologists call the cosmological horizon. Their light will never reach us again. Eventually, every galaxy outside our local group will pass beyond that horizon. A civilization in the far future, looking out at the sky with the most powerful instruments imaginable, would see a universe that looks almost empty. Our entire local group of galaxies will have long since merged into a single giant elliptical galaxy, surrounded by absolute void in every direction, no other galaxies visible. If they did not already know about the larger universe from historical records, they would have no way to deduce it. The evidence would be gone, swept over the horizon by the accelerating expansion. The universe is not just dying, it is forgetting itself as it dies. And yet even this is not quite the absolute end, because quantum mechanics introduces something called quantum fluctuations. Even in a state of perfect equilibrium, even in the deepest heat death, random quantum events can spontaneously occur. In an infinite amount of time, which is what heat death provides, even the most improbable events become not just possible, but inevitable. In the late 1800s, physicist Ludwig Boltzmann proposed that in a sufficiently old universe at maximum entropy, random thermal fluctuations could spontaneously produce, purely by chance, any configuration of matter and energy that the laws of physics allow, including, given enough time, a fully formed brain with a complete set of memories and experiences, assembled entirely by chance from the random fluctuations of the void. These hypothetical minds, developed as a thought experiment from Boltzmann's statistical mechanics, are called Boltzmann brains. They are not a prediction but a consequence, a logical endpoint of taking statistical mechanics seriously over infinite timescales. If the universe persists long enough in a state of maximum entropy, Boltzmann brains are not just possible. They are guaranteed to occur infinitely many times in the infinite future. Whether those minds experience anything, whether there is something it is like to be a random fluctuation of maximum entropy in a dead universe, is a question physics cannot answer. What physics can tell us is this: the universe we observe, with its stars and galaxies and planets and life, is profoundly unlikely from a statistical standpoint. A universe this far from equilibrium, this structured, this full of gradients and complexity and activity, should be extraordinarily rare compared to the vast blank timescales of maximum entropy that flank it on either side. We exist in a narrow window between the Big Bang and the heat death, a window that, measured against the full timeline of the universe's existence, is almost invisibly thin. This is the thing that the heat death of the universe really means when you fully sit with it. It is not just that everything ends, it is that the ending is so vastly disproportionately longer than the beginning that the word ending does not capture it. The era of stars and planets and life and thought will last maybe 100 trillion years. The era of cooling white dwarfs will last maybe 10 to the power of 37 years. The era of black hole evaporation will last maybe 10 to the power of 100 years. And after that, the era of heat death lasts forever. Every moment of complexity, every civilization that has ever existed or will ever exist anywhere in this universe, happened in the opening fraction of a fraction of a fraction of the total timeline. Not at the end of time, at the very beginning of it. There is something almost unbearable about that, if you let yourself feel it. Everything we call history, all 13.8 billion years of cosmic evolution, all the stars that have burned and the planets that have formed and the life that has crawled out of the oceans and looked up at the sky and wondered what it is, all of that is a brief warmth in the opening moment of a story that is almost entirely cold darkness. The universe spent a short, astonishing time being interesting, and then it will spend an eternity being nothing. But here is the thing. The fact that we are here to know this is extraordinary. The laws that guarantee the heat death of the universe are the same laws that made our existence possible. The second law of thermodynamics, the law that says entropy must increase, is also the law that drives every chemical reaction in your body, every thought in your mind, every beat of your heart. You are, in a very direct sense, a consequence of entropy increasing. You are part of the universe's unwinding, and the fact that this unwinding, on its way from the Big Bang to heat death, passed through a phase complex enough to produce beings who can understand their own fate, is something that the physics does not require and does not explain. The universe is 13.8 billion years old. It will persist in some form for a time so far beyond that it has no name, and in all of that time, the window in which anything like us could have existed is extraordinarily small. We are not an afterthought of the cosmos. We are a very early chapter in a book that has barely begun. Look up at the night sky. Every star you see is burning its fuel. Every one of them is moving, slowly and inevitably, toward the cold. The light reaching your eyes left those stars years, decades, centuries ago. Some of those stars may already be dead, and you would not know it yet. What you are looking at is not the universe as it is. It is the universe as it was, a brief record of warmth in something that is mostly cold, and mostly dark, and mostly nothing. And consider what it means that you can look at it at all. The era we live in, the stelliferous era, the age of stars, is the only era in the entire history of the universe in which anything like a living observer could exist. Before the stars formed, the universe was too hot and too simple for chemistry. After the stars die, the universe will be too cold and too dark for chemistry. The window in which stars exist, in which planets form around them, in which liquid water is possible, in which life as we understand it can arise, is a finite window. We are inside it. We are a product of it. Every form of complexity that has ever existed, every galaxy, every planet, every organism, every thought, is a consequence of the universe being in this particular narrow phase of its long decline from order to disorder. When the last red dwarf finally dies, roughly 100 trillion years from now, the window will close. Whatever lives in the universe at that moment will watch the last light go out, and the darkness that follows will last so much longer than the light that the light will seem, in retrospect, like it barely happened. We are not late to the universe, we are extraordinarily early. The age of stars is young, and we are alive in it. There is a concept in cosmology called the cosmic perspective. It is the attempt to understand human existence in the context of the full scale of time and space. Most of the time, the cosmic perspective is humbling. It reminds us that Earth is a small rock, that the Sun is an ordinary star, that the Milky Way is one of perhaps 2 trillion galaxies in the observable universe. But when applied to the heat death, the cosmic perspective does something unexpected. It makes our moment feel not smaller, but stranger and more precious, because the full timeline of the universe is almost entirely cold darkness. The brief warm window in the middle, the window we inhabit, is the anomaly, the exception, the rare and unlikely phase in which the laws of physics permitted something as complex and improbable as a living mind to exist and look outward and ask what it is looking at. Most of the universe's timeline contains nothing capable of asking that question. We exist in the fraction that can. That is not a small thing. That is perhaps the most extraordinary fact in the entire history of time. It is beautiful, and it is not permanent. Nothing ever was. If you enjoyed this video, consider subscribing. I will see you in the next one.